Today we'll be talking about the implementation and evaluation of a new classroom-based learning model called collaborative learning. Which seeks to address the some of the criticisms of the traditional lecture-based learning model, which has been criticized repeatedly for having, being too top-down and having insufficient feedback mechanisms. That is, that lecturers do not actually know whether their students are absorbing anything they're actually saying during the course of a lecture. The basic approach of which we have adopted is that of a discovery-based model. That is, that we have groups of students who are separated into, say, teams of 4, and they have to reach some expected knowledge, which we want them to discover by themselves from some base prerequisite knowledge. And as instructors, we have to guide them to this knowledge using a set of guide questions. And once they have discovered something, we integrate that back into their base content knowledge, evaluate it, and make sure they can use it for the next step of the process of discovery. A more detailed diagram of the model has been devised, and we will show it here. It's pretty straightforward. It's a UML based diagram. That is, that you introduce a topic, the topic which you will be covering, and the first thing you do is you check whether all the students have a prerequisite level of knowledge. You do that by generally asking questions of a very basic nature, which they're expected to answer relatively quickly. If they don't have this prerequisite knowledge, obviously you have to go back and make sure they have, your bases are covered before you proceed. In the normal flow of things, the next thing you would do is you would present the given problem. So if you're teaching graph theory, for example, you might want to introduce the problem of universal sink and give them a very basic problem related to it, and make sure the problem is clear. If it's not, you clarify it. And once you're sure the problem has been understood by all groups, you present them with a set of guide questions and begin the process of moderation. Moderation is basically where you make sure that collaboration efforts of each individual group is going on track. That is, that generally speaking, sometimes there is a very incorrect way of proceeding about solving a given problem, which for sure will not necessarily work. In which case, you can steer them back in direction, in the right direction. And normally, if the students manage to discover this knowledge, well and good. But if they don't discover, and we will get to what happens then. But if they are failing to discover this knowledge, as a lecturer, it is your responsibility to give them additional guide questions. And if even that does not work, you present them with things called analogies. And if that does not work, then in that case, you as a lecturer know that your pedagogical content needs to be reworked. That is, the students either do not have the prerequisite knowledge, you misjudged the level of prerequisite knowledge, or your guide questions are simply not good enough to lead them to the knowledge. The onus is, you'll notice here that the onus is on the instructor to make sure the students understand everything, and immediately whether or not they actually have that knowledge during the course of the lecture, rather than waiting for some sort of quiz or exam for any discrepancies to show. Generally speaking, once you have them, there are two kinds of knowledge which you want them to discover. There is explicit and implicit. The explicit knowledge is precisely what you would like them to discover. That is, for example, an algorithm to find the shortest path in a graph, given a source vertex and a destination vertex in n cubed time. That's something you'd want them to discover. Whereas implicit knowledge is a secondary goal, which you would like to use to evaluate the level of collaboration and depth of understanding that the students have reached in the process of in the process. So, for example, if students talk about the space complexity and you know actual implementation of the model, implementation of the algorithm, then you would be in a better suited position to, when you're paying attention to this, you'd be in a better suited position to determine their level of understanding. So we implemented some of this pedagogical content in an experimental course being taught at the University of Engineering and Technology at Lahore at an undergraduate level in a classroom of around 26 students. We taught both graph theory algorithms and dynamic programming, and these are some of the topics we taught in graph theory. But what we'll do is I'll hand it off to Wajiha, and she'll be telling us a bit about.
While teaching dynamic programming, a couple of topics that we covered are the knapsack problem, the change problem. We talked about maximizing the profits, maximizing the weights, maximizing the number of weights, and then we had the activity selection problem, in which we talked about maximizing total merit with start time and finish time, and we had total merit, maximizing total merit when only duration was fixed, and then maximizing the total utilization and the total number of activities. We also discussed the partitioning problem and the matrix chain problem. When the experiment was conducted in the class of algorithms, we realized that there were a couple of areas where the pedagogical content for our collaborative learning model needed to be revised, and so we went back and looked at those specific areas. In the midterm that the students were tested in the midterm that was given to the students, they were tested on dynamic programming. These were a couple of questions that we asked. They were asked to devise recursive formulation and draw a recursion tree. Then they were asked to come up with the complexity of the recursion tree and then draw a directed acyclic graph. These are the results. The results generally show us what were the problems that were faced. We see that most of the problem is faced in part 3, which is the complexity of the recursion tree. This we even faced in the class when the students were discovering the algorithm. We realized that students did not have a good practice with coming up with time complexity for the recursion tree. Also, we realized that some of the problems that we faced in question number 5, which was basically to devise an algorithm, give an output, and then come up with the complexity and do the same algorithm with the greedy approach. The results here were reasonably good, but we realized that again the problem was faced in time complexity and the greedy approach. Some of the reasons that can be looked into for finding out where the problem lies can be in the fact that maybe these concepts where the prerequisite knowledge was not clear, some of the implicit goals were not reached, so a further understanding, a further revision of the pedagogical content can lead to better results.